All right, this video is going to focus on electron configurations. Electron configurations came about as a way to put some practicality behind quantum numbers. And there are three main rules that electron configurations follow. The first is Aufbau's rule, that when electrons are moving into orbitals, they're always going to go from orbitals of less energy to ones of greater energy. So they always fill up the orbitals that require the least amount of energy before they're able to move on. And so when all the electrons for a given element have been placed in those lowest possible energy levels, that would be its ground state, and that would be its most stable energy state. An excited state would come about when an input of energy is able to move an electron outside of its ground state to a higher energy level than it would normally be found. The second rule, which is Hund's rule, we saw how as you get further into your electron configurations, things can get a little more complex because you can have multiple orbitals within the same energy sublevel. Hund's rule states that when you have orbitals like P, D, and F that have more than one orbital of the same amount of energy, you're going to put an electron in each of the empty orbitals before you go back and pair them up. So caring and sharing is the best way I can describe Hund's rule. Pauli exclusion principle is the third rule we're going to look at, and it's that orbitals cannot hold more than 2 electrons at any given time. Electrons are negatively charged and they repel one another. When they are in the same orbital, they spin in opposite directions so they can minimize their contact with one another. And it's that rule which allows the electrons that are in the same orbital, they would have the same quantum numbers for N, L, and ML, but they would have a different MS because of that spin. So this is one way to be able to know how to fill up your electrons from lowest energy orbitals to higher energy orbitals by following those diagonals. You'll see the S's are together, the P's, the D's, and the F's. But I don't intend for you, even in a normal year, to memorize that order of configurations, because you should be able to use your periodic table to see those relationships between the energy levels and the sublevels and those orbitals. Every row is starting a new energy level, and the lowest energy state of that sublevel would always be an S. So every row starts a new S for that particular energy level. And on the right-hand side of our table, that's when we're going to be filling in our P sublevel. In the middle, in our transition metal, we'll be filling in our D sublevel. And then finally, the lanthanides and actinides would be in our F sublevel. Remember that your N determines how many possible L's you have. Your first energy level can only have one sublevel. Your second energy level can have 2, which is why you have both the S and the P. Your third energy level can have 3 sublevels, S, P, and D. Your fourth energy level can have 4 sublevels, S, P, D, and F. But you'll notice that we go back on this from 4S, we move from 4S to 3D, and then we go in and fill up 4P. And the reason why we kind of go back with both the D's and the F's is, remember that Aufbau's rules, the first and foremost, is that you always place electrons in energy levels from lowest to highest energy. Well, 3D happens to have just a little bit more energy than 4S, but not as much energy as 4P. And so that is why we have to fill up the 4S orbital before we can fill up our 3D orbitals. So we do not go in order numerically of energy level, but in order of energy requirements, lowest to highest. You can have configurations come in a couple of different forms. You can have them written where you see the specific amount of electrons that are within a sublevel. That's your ground state configuration. Because these configurations are always going to follow the same pattern, sometimes as you get further up, it makes more sense to write a noble gas configuration, a shortcut configuration. And then finally, you can have your orbital diagrams where you're visibly seeing those electrons placed in orbitals within a sublevel. So we're going to look at this for an element that's going to place its final electrons in S, P, D, and F. We're going to start with argon. Argon is number 18 on your periodic table. All S sublevels, because they have one orbital, can hold 2 electrons total. Any P sublevel has 3 orbitals, so it can hold a total of 6 electrons. Ds have 5 sublevels, so they can hold, or 5 orbitals, so they can hold 10. And F sublevels have 7 orbitals, so they can hold up to 14. Remember, if we go back to the beginning of our periodic table, we want to put our first 2 electrons in 1s. We move into our second row on the table, so then we would put the next 2 in 2s. And then the final 6 would be on the far right-hand side, which would be 2p. If you add those superscripts together, you get 10 of argon's 18 electrons. We would have 8 more to go, and that would be in period 3. So 2 would go into 3s, and 6 would go into 3p. The noble gas configuration is determined using the last filled energy level, the last row on the periodic table that you made it all the way through, and then you would put the noble gas in brackets to represent that your element or ion has the same configuration as that noble gas. And so in argon's case, our noble gas would be neon. And then we would continue. Neon has 10 electrons. We need to place 8 more, and those 8 would be the final part of argon's configuration, that highest occupied energy level, which was 3. So the electrons in 3s and the electrons that were in 3p. Argon is a noble gas, and noble gases are very unreactive. And hopefully you can see why, because all of the orbitals in which argon has placed electrons are completely filled with those electrons. They are at max capacity. If you added any more electrons, you would have an unstable form of argon. Noble gases are non-reactive, primarily because they have all of those orbitals filled as much as possible. Our next example is zinc. Zinc, I believe, has 30 electrons, so its ground state configuration is going to look a lot like the one we just did. But because it has another 12 electrons past argon, we would move into our 4th row on the table and put 2 of those remaining electrons in 4s. And then because we are in that middle section, the transition section of our table, we would start our D sublevels. Our first D sublevel is found within the 3rd energy level, so we would have 3D. And zinc has 10 more electrons to place, and that's the number of electrons that these can hold. So you would have 10d electrons in that 3rd energy level. The noble gas configuration this time again is going to be the noble gas that ended my last filled energy level, my last filled row on the table, which would be 3. So that would be argon. And then the remaining 12 electrons that zinc has beyond argon would follow based on where the electrons need to be added from, in this case 4s and 3d. And if I do the diagram showing the electrons being placed into boxes, remember all s's have 1 orbital, so 2 arrows can fit into any s. P's have 3 orbitals, so they can hold up to 6 electrons. Ds have 5 orbitals, so they can hold up to 10 electrons. Strontium is going to have, I honestly don't recall how many electrons strontium has. I know it has a lot. Give me a second, I'll do some math for you. 10, 18, 20, 30, 38, I believe is what we get here. So you would have moved past your 3D. I'm sorry the 6 moved to the bottom there. You would have your 10 in 3D, then you would need to place 8 more electrons. The next 6 would go into 4p, and the final 2 would go into 5s. So the noble gas that we would use this time would be the noble gas at the end of period 4, which in this case would be krypton. And then you would have 2 electrons left to place. Those would both go into 5s. And the reason that your alkali and your alkaline earth metals are pretty reactive is because they have just started the beginning of a new energy level. And the whole goal, what elements are trying to achieve, is a stable configuration. So they will lose, gain, or share electrons to make that configuration. So in the case of strontium, it would be more than willing to give up both of its electrons to have that filled 4th row and have a filled 4th energy level. Our final one is lanthanum, and I know lanthanum is pretty far down on the periodic table. If you add all of those subscripts together, you will get lanthanum's atomic number, which tells you the number of electrons it has. The noble gas that would be used, again, would be the end of the row before we started that had lanthanum in it, and that was the 5th row. And I believe the noble gas for that one is going to be xenon. And we only had 3 electrons left to place past xenon. The 2 would be in 6s, and then only 1 would be found with 4f. And if you really want to go crazy and draw out all those arrows, go for it. You'll notice that all of the sublevels are completely filled except for the last one in which electrons are placed. And here, because you only had 1 electron in 4f, only 1 arrow is found in a 4f orbital. You can also have positive and negative ions in which you write configurations. If you are a positive ion, you've lost electrons. If you're a negative ion, you've gained electrons. So potassium, instead of having 19 electrons, would lose 1 for that positive charge, and it would have 18. And this is, again, just additional justification for why your alkali and your alkaline earth metals lose electrons while your nonmetals gain electrons. They are all trying to become like the nearest noble gas. So potassium being where it's at on the periodic table, we would want to find the noble gas through the 2nd period, which was neon. We had 8 electrons left to place, so this should look a lot like argon. 2 would go into 3s, 6 would go into 3p. There are exceptions to these configurations. We see those exceptions primarily in the transition metal section, basically because of the sheer number of orbitals that are available within that D sublevel, and then with the inner transition metals and the lanthanides and actinides, there are multiple configurations that will result in stable ions. And so with that in mind, we can, or stable elements, period, whether they be ions or atoms. And so with chromium and with copper, rather than having 1 empty orbital, in the case of chromium and its group members, it will borrow 1 electron from 4s so that all of the 3d orbitals and the 1 4s orbital contain an electron. While copper is going to be 1 shy of having the 3d sublevel completed. And so whether it makes more sense to leave 1 of the 5 orbitals open in D versus S. Energetically wise, it is more stable to have that electron be with the D sublevel to have those 5 orbitals completely filled. And that truly does finish off the 3rd row, the 3rd energy level, since that was the last sublevel that was available in which electrons can be placed. So again, those are just exceptions. I don't expect you to know them, but just wanted you to know how they come about. And the last little piece we're going to talk about in this section are valence electrons and core electrons. Valence electrons are the electrons that are found in the highest occupied energy level. So with a noble gas configuration, it would be whatever electrons that you have placed in the row that element is placed on the table, the s electrons for that row, and any p electrons for that row. These are the electrons that are involved in bonding. And so every element within a group on a periodic table shares the same number of valence electrons. Group 1 will all have an S1 electron, so they would have one valence electron. Group 2 would have two S electrons, and so it would have two valence electrons. All of your transition metals are going to stay at 2 as well, but the reason why the transition metals can form multiple stable ions is because they have lots of empty d orbitals in which their electrons can be arranged. As we move further across the table, group 13 can have up to 3 valence electrons because it has the 2 from the previous S and 1 in P. Group 14 can have 4 because it now has 2 p or electrons. Group 15, 5. Group 16, 6. Group 17, 7. And all but helium in group 18 can have a maximum of 8 valence electrons. Again, that's what they're shooting for, beg, borrow, and steal to get to their 8. Helium would be the exception. It only has 2 electrons. The core electrons are the electrons that are not a part of that outermost valence shell. They are separating the nucleus from those outermost electrons, and we'll get into that with periodic trends, but they are not involved themselves in chemical reactions. So here I want to know how many unpaired electrons are found in the ground state, O, O plus 2, and O minus 2, and which of these ions are paramagnetic and which are diamagnetic. So to find unpaired electrons, you need to look at your the last part of your configuration in which electrons are being placed, because again, you do not move from one sublevel to the next until you have completely finished off that sublevel. So if we take a look at oxygen, it has 8 electrons, and so it would have 2 and 1s, 2 and 2s, and then 4 and 2p. Only the 2p is the one that I need to look at to determine the unpaired electrons. I would put one in each of the 2p orbitals, and then I would pair up one of those electrons with the fourth 2p electron. The other two would not have an electron that they are sharing their orbital with, and so there would be 2 unpaired electrons. So because there was two electrons that were unpaired, this would be considered to be a paramagnetic atom. With O plus 2, you're losing 2 of the electrons that oxygen normally has. You would be down to 6. So you would have 2 in 1s, 2 in 2s, and 2 in 2p. Remember, each of the p orbitals can take an electron before they pair up. So you would have 2 unpaired electrons in this particular example as well, and it too would be paramagnetic. With O minus 2, you're gaining electrons, so rather than losing 2, you're gaining 2. So we would take that original configuration and fill up the remaining 2 spots in 2p. At this point, you have all of the electrons have a partner, so there are not any unpaired electrons, and this would be considered to be a diamagnetic ion. And then our final part of this video, which the following configurations would correspond to a ground state, and then if they don't, which of these would correspond to a ground state, identify the atoms, and write the ground state configurations for those that do not. So here you have 1s2, 2s2, 2p6. We do take care of 1s, and then we move on to 2s, and then we move on to 2p. So this is a plausible configuration. We have 10 electrons total, and the element that has 10 electrons is considered to be neon. Here in part B, you have 2 electrons again in 1s, 2 electrons in 2s, but I want you to notice that you have 4 in 2p, but then you've moved on up to 3s. So one of those electrons has gotten excited. This would not correspond to a ground state. We would have to rewrite it by moving that one electron in 3s back to 2p. And if you do that, you would get fluorine as your answer.